Before continuing, let us consider an example. Suppose the box length along x direction A is 200 picometer and B is 100 picometer. And let us consider the probability of finding this particle in a smaller size box. Probability inside a box. Box with A1 40 picometer, A2 60 picometer, and B1 20 picometers, and B2 30 picometers. So vertically, the lower corner is 20 picometers, and the upper corner here is 30 picometer. Horizontally, the right corner, the lower right corner is 40. Sorry, this lower left corner is 40 picometers, and lower right corner is 60 picometers. And the question is, what is the probability of finding this particle inside this region? All right? This is the general definition, all right? For a very small volume, the probability is without the integration sign, this expression. But if the volume is a larger volume, then we have to add up, which means we have to integrate. In this problem, we have how many dimensions? 2 dimensions. So in our problem, it's a 2-dimensional integral. And the volume of integration is just this box here. Maybe I will write this again later, but I need some space on the blackboard. So probability is our variables are x, y. This is a rectangular region. X goes from A1 to A2. And y goes from B1 to B2. This expression is going to give us the required probability. Okay? Now, this is a double integral. However, it's a simple type. Why? Because this factor contains only the x variable, the second factor contains only the y variable. Therefore, this integral is factorized. So we have integral with respect to x times integral with respect to y. Integral with respect to x is this is square. In our problem, all functions are real functions, no complex number I. Therefore, star is the same as itself. And as a result, squares. So this is A1. What is A1? 40 picometers up to A2, which is 60 picometers. And the other factors for B1 is 20, B2 is 30 picometer. Now, for the ground level, the x factor is 40 to 60. 2 over a times sine pi over a x square. This is our expression. And for ay, it is 2 over b from 20 to 30 sine square pi over b y dy. Remember, value of A is given 100 picometer, B is 200 picometer. So we do these integrals. And we have to do the integration and then put the limits and then multiply the constants. For n equals 1, for both of them, I found 0.1. For this one also 0.1. And then the probability is simply 0.1 times 0.1, or this is 1%. 0.1 times 0.1 is 0.0. 1. And in percent format, it is 1% probability. So in the ground state, probability of finding the particle inside, anywhere inside this tiny box is 1%. What is the probability of finding the particle outside of this smaller box? 99%. 99%. The remaining, because the total probability is for the entire box has to be 1. Okay. Let us turn back to the energies and the corresponding state functions in this problem. Let us consider a special case. And the special case is when the value of A is the same as value of B. In that case, the two sides are going to be equal, and we call it square box, square, using the geometric term. Then these parameters, fx and fy, these are energy parameters. They are the same. Notice, if A is the same as B, fx will be same as fy. And call this, drop the xy subscript for simplicity, just call it f's. In this case, possible energy, our energy formula, which is this, we can write it as, because fy and fx are the same, we can factorize it. So it is f times nx plus nx squared plus ny squared. This is our simplified expression if we are considering a square box. All right? Now, let us show the lowest few energies using an energy level diagram. So this is energy. Say this is 0. Now, lowest energy, of course, is selection of nx and ny to be 1. So this gives 1 plus 1, 2f's. So here we have, this is nx equals 1, ny is also 1. This is the lowest level. Now, the next level, higher in energy, is we may select nx to be 1 and ny to be 2. In that case, 1 plus 4 makes 5. 5 epsilon. But we could also select nx to be 2 and ny to be 1. And we are going to obtain the same number, isn't it? Now, for the first selection, the total state function is psi 2, 1. Psi 1, 2. The first index is for nx, the second index is for ny. Now, if you look at this expression, Remember, A is the same as B, but that's a constant, that doesn't matter. But here, this is 1 here, this is 2. For the second selection, it is 2, 1. Now you ask yourself, is this function same or different than that function? Why? Because each different function, state function, means a different state. Therefore, you have to make sure, you have to compare if they are same or different. If they are different, we are talking about different states. Psi 2 a constant, that times that, in fact, it is the square of it, sine pi over a x times sine 2 pi over a y. Remember, a is the same as b. Okay? This is 1, 2. Psi 2, 1, same constant, but this time the x factor has 2. And the y factor has 1. Now, are these two functions same? Just imagine their graphs. Or just take any value for x inside the box, any value for y. For the same selected x, y values, you calculate this expression and calculate that expression to see if they are the same or different. In general, what are you going to find? Are you going to obtain the same numbers? Say for this problem, select x equals 40 picometers, y equals 20 picometers, for example. Use this number in this expression for x and for y. Calculate it. Repeat the calculation with this expression. Are you going to obtain the same numbers? No. All right? Therefore, these two functions are different. In other words, even though the energy values are the same, 5 amps, the state functions are different. This is called degeneracy of the energy level. So we indicate by 2 dashes here. This is, say, 1, 2. This is 2, 1. So the concept is this: degeneracy of an energy level. Is the number of state functions with same energy. The standard symbol is G. It's a standard symbol, which means in many textbooks you examine, you are going to, when you see small g, textbooks about quantum chemistry, of course, the symbol small g indicates degeneracy of the energy level. It is a number of state functions. In this problem, how many states do we have? Is it possible to obtain another state functions Or is there another selection so that you will obtain 5 Fs? No. That's for 5 Fs, only 2 possibilities. One is nx1, ny2, the other is nx2, ny1. So, how many state functions do we have with the same energy over there? 2. We say that degeneracy is 2. So here, we write, for the ground level, is it possible to obtain a different function or a different selection to get 2 Fs? No, there is only one possibility, right? Therefore, ground state has G equals 1. Okay. Now, the term degeneracy, all right? There are just 2 possibilities for an energy level. Either G is 1 or G is larger than 1. Just 2 possibilities. If G is 1, we use the word non-degenerate. If G is larger than 1, we say degenerate. The number of state functions that have the same energy, which we call degeneracy, but we also use such terms. If G is 2, we say the energy level is doubly degenerate, because doubly degenerate. If there is more degeneracy, which means if G is larger than 2, for example 3, we say the energy level is triply degenerate. If it is 4, we say quadruply degenerate. These are the terms, words we use for numbers. So if a level is quadruply degenerate, it means G is equal to, what is the numerical value? 4. Words related with numbers, all right? Let us look at the next allowed energy level. If we select uh, 1, 3, in fact, let's make it is easier to make a table, list of values. Let us do that. Because our energy formula is Fs times nx squared plus ny squared, it is enough to calculate this quantity. This is 2. It means 2 times Fs. Now, 1, 2, 5, 2, 1, also 5. If I write 1, 3, 3 squared is 9 plus 1, 10. But 3, 1 will also give 10. If I choose 2, 2, I will have 4 plus 4, 8. Now, what do you see? After 5 Fs, what is the next energy level? Is it this one or this one? In increasing order. 8. So, the next one is 8 Fs. Is there any other selection of the integers which will give 8 Fs? No. Therefore, How many state functions are present here for this energy level? Only one, which means, is it degenerate or non-degenerate? Non-degenerate. G is 1. What is the next energy level? 10 EPS. But how many states are there? 2 states. 1, 3, when you use it in such expression, the state function for 1, 3 is different from 3, 1. Therefore, there are 1, 2 levels here. This is, therefore, this energy on EPS, 10 EPS, is it degenerate or non-degenerate? Degenerate. What is the degeneracy in number? Doubly degenerate, or G is equal to 2. If you imagine all possible energies, higher energies, what do you conclude? Maximum degeneracy you will expect is how much? 2. There can be no higher degeneracy. Maximum is 2. But for higher energies also, if Nx is the same as Ny, the level is going to be non-degenerate. For example, 3, 3. 3, 3 will have energy 9 plus 9, 18. 18 EPS. That will be non-degenerate. So the degeneracy here is either non-degenerate levels or doubly degenerate levels. Let us mention briefly what would happen if this particle were in a three-dimensional box, which is the three-dimensional space, like such a box inside it. Let us keep the similar notation. This is, of course, origin. Along the x direction, the box size is A. Along the y direction, the box size is B. So this rectangle on the xy plane is just what we have discussed for the particle in two-dimensional box. Here, the only difference is there is a third dimension, and let's call this C. All right? And we have a particle inside. A free particle. This particle is free. There are no forces. However, it is trapped. It has to be inside the box. It cannot penetrate. How many dimensions is it moving in? 3 dimensions. Therefore, how many variables are needed to locate its location? 3 variables. Because the box has a rectangular shape, it is preferable to use Cartesian type variables. For example, this box could have a spherical shape. It is possible to use a spherical shape box. In that case, we would have preferred polar type, spherical polar type variables. All right? Remember, when the number of variables is more than one, there is always a need for selecting the type of variables to describe the problem. Number of variables cannot change. Number of variables, for example, here is how many? 3. But the type of variables that you use could change depending on the shape of the volume. Here we have a rectangular volume and Cartesian type variables is preferred. So we have variables are x, y, z. Hamiltonian, kinetic plus potential energy. But the potential energy is constant here because we are saying that it's a free particle, which means there are no forces. If force is 0, potential energy is a constant. And the value of potential energy is arbitrary, so we select any value for it. In this problem, we just choose 0 for the value of that arbitrary constant, as before, all right? So it is just kinetic energy. What is kinetic energy? Same as before. However, the square of linear momentum, now the linear momentum has how many non-zero components? 3 non-zero components. This is a motion in 3D. Therefore, this is or just expand it. And the problem is solve this equation with this Hamiltonian. What is the meaning of px square? Explicit definition. It is minus h bar square times second derivative. Second derivative is with respect to what is the difference of this term from this one? The variable is different, isn't it? As similar for this one. Okay. Now, this part, you see this structure. 1, 2, 3 terms added. Next, you examine each individual term. This, in terms of which variables does it contain? This term contains which variable? X variable. Does it contain y or z also? No, only x variable. Remember, x, y, z are independent variables. Contains only x variable. What about this one? Contains only y variable. And this one contains only z variable. Therefore, we may imagine this mathematical problem of 3 variables as if there are 3 non-interacting fictitious particles moving, like this. Hx is this term, hy is this term, hc is that term. 3 independently moving, non-interacting, fictitious particles, because there is only one real particle. The real particle is moving in 3 dimensions. But the fictitious particles, there are 3 of them. There is an x particle, a y particle, a z particle. X particle is moving only along the x direction, which means it's a particle in a one-dimensional box. Y particle is moving only along the y direction and independent of what the x particle is doing. Similarly, the z particle is moving along the z direction between 0 and c. Each fictitious particle is a particle in 1D. So, the total energy of the three fictitious particles is the energy of the real particle. So this is sum of energy of x particle plus y particle plus z particle. And the state function is product of psi x times psi y times psi z. What are the allowed values for the energy of the x particle? What is x particle doing? Moving in a one-dimensional box. With what is the size of the one-dimensional box for the x particle? A. So this is just fx times, where nx is 1, 2, 3 at any number, and the definition of fx is similarly Ey, the fictitious particle which we call y particle. What is it doing? It's also moving along one-dimensional box. But what is the box size for the y particle? B. So this is similarly z particle. All right. So, the number for Ex in this total energy is any number which obeys this relation for a certain selection of Nx. The number for Ey in this expression is any number which obeys this relation, which means you have to select only these numbers for ny. Similarly for nz. The selections of nx, ny, nz are independent. All right? Any selection of nx, ny, nz according to those rules is an allowed value for the total energy of this particle, physical particle, moving in 3 dimensions box here. So the total energy need to be given some subscripts here. We need 3 subscripts to indicate what is nx, what is ny, what is nz. Nx, ny, nz. So making it more explicit here, we may write Enx plus Eny plus Enz. Enx will be this expression. Eny will be that expression. Enz, that one. For example, E1, 1, 1. What does it mean? The lowest possible energy, which means ground energy level. It means select nx equals 1, ny equals 1, nz equals 1. Then what is the energy? Fx plus fy plus Fc. This is the lowest possible energy. In this problem also, let us ask, is there a 0-point energy here in this motion? When we say is there, we mean there are just two choices, either yes or no. What is the criterion? No means 0. Yes means non-zero. Is this number 0? No. Because those energy parameters, Fx, Fz, are non-zero numbers. Remember, this problem also has only kinetic energy. Classically, even if the particle is moving in 3 dimensions, what is the lowest possible value you expect for the kinetic energy? 0. The particle can just be not moving classically. All right? In that case, its kinetic energy will be 0. So there is a difference between classical expectation for the lowest, between classical expectation and quantum result. This is the quantum result for the lowest energy. And one is 0, the other is non-zero. This is by definition 0-point energy. So translational motion has a non-zero 0-point energy, and for the 3-dimensional case, that expression gives you the 0-point energy. Let us consider a special case, just as we did with the square box. If this box is a cube, all right? What is the property of a cube? All sides are equal, which means A is same as B, same as C. If this 3-dimensional box is not a cube, if A is different from B and B is different from C, all A, B, C are different from each other, then for each selection of nx value, ny value, nz value, you would obtain a different number for the total energy in general. That means each energy level will have just one state function. Okay? And if there is only one state function for a given energy level, what do we say about the degeneracy of the level? Only one function for the same energy, non-degenerate. So if the box size A, B, C are different from each other, in general, all the energy levels will be non-degenerate. But if A then all will be the same. Look at the expressions. The only difference is A, B, C. Call this Fs. Then the energy expression will be this. And if you make a table I have changed one of them. This is 4, 5, 6. But instead of changing the third quantum number, I could also change this one or change this one. This means in both cases, in all of these 3 cases, I will obtain the same number, isn't it? 6, which means the total energy is 6 Fs. So up to here, we are finished. In an energy level diagram, this is 0 here. There is a level 3 EPS. This is lowest level, non-degenerate. But the first one, excited energy level, this is 6 EPS. How many levels? How many states? 1, 2, 3. Because this selection for Nx, Ny, Nz will give a different state function. State function is product. X factor times Y factor times Z factor. All right? This selection will give a different function than that selection, than this selection, which means there are 3 state functions, different state functions, all with the same energy. So the energy level, we say energy level is degenerate. Inverse, how do we describe it? Triply degenerate. We may continue for higher energies. So this problem will contain maximum of triply degenerate states.